Hello and welcome to the ARAMIS webinar. My name is Justin Bushinsky, and I'm a technical account manager for Trilion Quality Systems. I'll be your host and tour guide for today's event. I'm on location just outside of Philadelphia at Trilion Quality Systems headquarters, where we plan to explore optical metrology with a focus on testing for automotive groups. The Trilion team of engineers here will be showing us their most robust optical solution, ARAMIS, and highlighting its simple setup, high accuracy, and its harmony with simulation software. Maybe you've heard about this type of technology in research, but not like this. This is a tool designed for technician-level operation. So buckle up as we take an automotive application tour with Trilion and the ARAMIS 3D optical measurement tool.
Hello everyone, and welcome to our webinar on automotive testing advancements with ARAMIS optical strain. We thought to make this webinar because change is the new constant for automotive. And with top trends of autonomous vehicle, electric vehicle, and connectivity, the industry has competition and disruption bearing down on them. At the forefront of these changes are the systems and methodologies that companies are using to validate and test their materials and components. Our automotive customers report that the design challenge to deliver safety and reliability has never been more important, and they are increasingly under pressure for their time to market and cost of testing. Trilion has a time-saving and cost-effective solution to this challenge with its non-contact measurement tool, ARAMIS. ARAMIS has the ability to measure holistically, simply, and rapidly. So let's take a look. Today I'm visiting Trilion's headquarters in Philadelphia. You can see there are offices throughout North America. Contact us to meet your local office representative. If you are working in automotive, there's a good chance that someone you know has been exposed to our technology, and Trilion's footprint continues to grow. Trilion is the distributor of GOM products and an American engineering firm. They develop non-contact 3D measurement and analysis tools. Here you can see the lineup of non-contact measurement solutions. Trilion is often helping customers with application development, performing consulting services, and deploying turnkey systems. These non-contact solutions have a place at every step of the product development cycle. Focusing on a few of the important steps today, we can identify topics where ARAMIS will answer those new challenges that the automotive industry faces. ARAMIS was a critical part of the Ford F-150 conversion to an aluminum body. Along that process, ARAMIS was key in understanding the material properties and the mechanical behaviors of the vehicle design. Its data served as inputs for the simulation and for further design developments. The powerful part of ARAMIS is that every test completed correlates with the simulation across thousands of points. Our agenda for today will be to cover these three stages of development and show you use cases in material and component level testing. So let's start with material properties.
Okay guys, we're inside Trilion headquarters, about to step into the lab. Before we do that, let's take a quick look at the ARAMIS. It comes in different configurations depending upon your application needs and budget, but the ARAMIS always has the same key features. Two cameras synchronized together, slightly tilted towards each other to see, just like your own eyes see, in 3D with that depth of field. But the ARAMIS sees much more than the naked eye. It has the capability to measure displacements and strain deformations with incredible accuracy. So let's go inside the lab. What's going on in the lab today, Joe?
I have an ARAMIS set up for material testing on our load frame.
This looks pretty cool. It looks like it's completely non-contact. You're just taking a measurement with just the cameras on the ARAMIS sensor pointed at the tensile coupon. Is that right?
Yep. I apply a speckle pattern onto our coupon. I load the coupon like normal into our load frame. And then that speckle pattern allows the software to track the full field strain across the surface. It's like having thousands of strain gauges across your surface.
Wow, okay. Well, if that's the case, then you must need a really good coverage of dots on the surface there. Can you show me how we would put that surface down?
Sure. Here you can see some samples we prepared. These were completed with off-the-shelf spray paint. We spray on a light coating of flat white paint and then speckle on flat black dots on top of it.
That looks, is that difficult to learn, to get used to like that?
It takes some getting used to, But if you prefer, we have stamps, rollers, and even printers that will print the pattern for you.
Okay, yeah, there's a lot of options there. That's great. Thank you.
You're welcome.
Okay, great. Can you show me a little bit of the setup now? Because I'm wondering if you're linked to the load frame with the ARAMIS in some way.
Yes, we are bringing in a cable out from the load frame into the ARAMIS controller, which you see here. This allows us to trigger from the load signal and synchronize all of our data together.
So I'm sure our viewers are wondering what type of material that you have here that we're testing.
This is a plastic sample that we're using today, but ARAMIS can be used for any material because of its non-contact setup. As long as it can be patterned and it can be monitored for strain and displacement fields in time.
So what about the geometry? Are we limited to just planar coupons such as this?
No, some other interesting geometry applications common to our testing involve cylinders during compression and welded joints loaded uniaxially for inspection of heat-affected zones.
That's really interesting. What about shear strain propagation? Could you handle something like that?
Yep, even shear strain. ARAMIS sees in 3D, so we will capture as much of the surface as we can see, measuring major and minor strains and directional strains, and we can get it all simultaneously across all those nodes of the speckled dots.
Oh, that's fantastic. I'd love to see a demo of this.
In the software, we can manually inspect and take a look at both live images of the entire surface in our part of interest. Once we have images here, we can then compute our surface and then take a look and see the 3D nature of it. Zooming in, we can see the mesh structure and all the data points we get across the entire structure of our surface. Once we have our surface computed, we can then do strain inspections across the entire surface of the part. We're now seeing the full field strain across the surface there. Now during the live acquisition of our test, as we're recording and pulling the sample, not only are we seeing the full field strains live, we're also doing a 2-point distance or an extensometer and getting a live readout of that as well as a max strain level across the entire surface. And then once failure has occurred, we just simply stop the measurement.
So ARAMIS is used to measure material response in applications ranging from simple axial tension tests to shear testing to even split Hopkins and bar tests. Let's take a look at a few. The ARAMIS measurement technique delivers higher quality data for materials testing and is unmatched by clip gauges or strain gauges. ARAMIS offers the potential for thousands of points of measurement on advanced composite specimens rather than the 2-point tracking capability featured by most video extensometers. The cameras are angled towards each other slightly to see just like your eyes see in 3D. In this way, we can track the pattern on the surface that the software automatically identifies. The pattern is optimized to be random, isotropic, and highly contrasting. You can see even if you end up accidentally spray painting a big black dot like I have in the center of the photo, you can repair the pattern with some white dot speckling. The software will recognize the pattern and divide it into a triangular mesh that you can see on the right side. Each node represents a discrete location where we can pull strain information, both principal and directional. The spray paint becomes thousands of strain gauges across the surface. Think for a moment about the time it takes to lay a foil strain gauge, set up an accelerometer or an extensometer, and now consider how you can spray thousands of 3D coordinates across your sample surface. We call this a full field measurement, and it tells a holistic story that can be intuitively understood just by viewing it. The ARAMIS has been certified as a class 0.5 extensometer according to ISO standards, or a B1 or higher extensometer according to ASTM standards. The data can also be overlaid into finite element analysis simulations, bridging the gap between simulation and reality. These full field measurements allow for examination of localized behavior and extraction of data at multiple distinct areas of interest. There is no inherent length scale to ARAMIS, where a clip gauge or extensometer will be limited by its gauge length. ARAMIS can capture both strain localization and the global strain, and it's this high strain necking area that is responsible for more accurate material properties, a crucial factor in simulations. In the same project captured by ARAMIS, we have high enough resolution or sensitivity to look at the global strain on the left of this notch test, or focus more closely on the right at the plasticity and cracking evolving at the notch. The ARAMIS allows us to track even high strain. Here is an impressive data set with a polymer, illustrating the capability to track highly deforming subsets of the pattern as we move continuously through the test. Although we are tracking the surface of the material, we often are able to understand the structure beneath as the ribbons of carbon-reinforced plastic reveal themselves in this composite material. If we can see it, we can measure it. And ARAMIS works well with mirrors. This is a first surface mirror that we've mounted in our field of view to be able to capture both the front and the back of this composite material. Have you ever wanted to capture both sides of your material? ARAMIS works very effectively as an input to your developing simulation model. The finite element model can be brought into the ARAMIS software, aligned and compared to bring the model ever closer to reality. This system is independent of geometry. So far we've only explored planar samples, but it is not an issue to explore cylinders or other more complex geometries. ARAMIS is also useful in measuring custom or non-standard tests. It is possible to track the speckle pattern during adhesive peel tests or shear tests, and ARAMIS is used often for sealants and adhesives, can easily track shear strain and other rotational measurements. When synchronized with load history data from the testing frame, the ARAMIS data can be configured to automatically plot the stress-strain curve and find material properties according to ISO ASTM standards. This can be configured as a technician's tool, minimizing the number of mouse clicks, but also the amount of training needed. The kiosk mode prompts the user for the steps of the measurement. The system is independent of temperature and can see through a chamber window to make strain measurements such as this, a tensile test of magnesium at 300 degrees Celsius. Our researchers have developed a partnership with infrared cameras to create an ARAMIS thermography module. An IR camera with trigger synchronicity is linked to the ARAMIS, and the thermal data can then be brought into 3D coordinates and mapped across the specimen's surface. The coupling of temperature and strain data often is a byproduct of the large temperature range of operational environments. Sometimes the functional integrity of the material may depend on the influence of temperature. This thermography module is useful in a dynamometer on the hot side of an engine, or to the powertrain group, measuring an exhaust manifold, for instance. It is also very useful in microelectronics. In this experiment, the temperature mapping is correlated with thermal expansion. If the user understands the material coefficient of the thermal expansion, ARAMIS can compensate and isolate the mechanical strain. The system is independent of time, measuring this high cycle fatigue test of a welded T-joint. In this experiment, the T-joint was rocked back and forth cyclically by the load frame, and ARAMIS captured at peak load times. Over the course of 20 hours, the T-joint crack began to open. The analysis here was done after failure. A virtual 2-point distance was placed down to monitor the crack opening, but only after discovering from the images where the crack originated. Sheet metal testing is an indispensable part of automotive production. The OEMs monitor their tool and die for forming severity of a stretched or draw product with our Argus technology, but our ARAMIS could tell them more. The severe forming that takes place in production cannot be understood through uniaxial testing. Biaxial dome testing, such as the Nagazima or bulge test, yield the material properties necessary to build sheet metal forming limit curves. The ARAMIS is mounted above the dome and shielded from the high pressure oil while the material is taken to failure over a series of tests. The ARAMIS is designed to take this data and automatically process it according to ISO standards. This results in a forming limit diagram such as this, a crucial predictor of material behavior for production quality. The system is independent of time, temperature, loading, and geometry. A user can set their own gauge length according to their application. ARAMIS is capable, unlike conventional tools, of measuring high strain area in an accurate way. It is non-contact, it's massless. ARAMIS will measure both local and global strains. It's capable of scripting and it features a kiosk mode. The most powerful benefit is its ability to overlay results with finite element models, making it an indispensable tool for materials research.
We're back on site at Trilion headquarters for a second round of testing. We now have a better understanding of the ARAMIS, its setup, interface, and its critical ability to provide input parameters into the simulation model. Let's now turn to product design. ARAMIS can also help develop input parameters for structural and component level testing. We're going to be exploring how ARAMIS can work on an actual vehicle. So let's step into the lab and take a look. Come on.
Now let's turn our attention to ARAMIS component level testing, where we can measure and inspect features from small to large all around the vehicle. Another way of tracking that the ARAMIS uses is point marker tracking. These are lightweight adhesive stickers that are optimized in size for your field of view. We feature them in different variations. Some are easy to take off, some are permanent, some are magnetic and reusable, and some are capable of withstanding high temperatures. Wherever you place one, the system will automatically find and track a 3D coordinate for displacements and vibrations. It's the high contrast that the ARAMIS recognizes. For engine work, ARAMIS engineers spray the component with black paint and roll on dots of white paint that you see there in the center of the screen. The point marker stickers along this prosthetic leg on the right side are being tracked in the image. Notice the stickers on the knee in the experiment. This section of stickers was selected by the ARAMIS operator as a rigid body, so the displacement of the blade is isolated from the overall motion. ARAMIS can make anything in its field of view relative to another. This is called rigid body motion compensation. Here is an example of a simulation being compared with ARAMIS full field reality. You can see the shadowy representations of the wired strain gauges in both the simulation and the ARAMIS on the right. The CAE department had predicted and instructed the test engineer where to place these sensors. The strain gauge data showed some deviation from the simulation, but the ARAMIS told the full story. You can see a splicing defect just out of reach of the strain gauge.
Hey Joe, how you doing, man? Looks like you've got some stickers here. What you up to?
Yeah, Justin, I'm putting down some target dots on this hood here. Each target dot is going to give me a 3D coordinate space that I can track and measure. You already saw that speckle pattern before, which is giving us that full field strain coverage. But each one of these target dots is going to give me discrete point locations that I can measure.
That's great. So you're measuring displacement with these dots then?
Exactly, yeah, we're measuring displacements.
Okay, cool. So it looks like you've got them all over the hood. And are you going to be tracking the movement of the hood?
Yeah, so actually what I'm going to be doing is I'm going to slam this hood down, and then I want to track the relative motion of the hood here.
Wow, that's pretty cool. It's going to be really fast. But you know, you have some dots here on the side. It's not even part of the hood. What's your reason for doing that?
Yeah, so I put these dots here on the hood so I can do a rigid body motion compensation. What that allows me to do is look at the relative displacements on the hood instead of the whole global motion of the entire car as I slam my hood down.
I see. When you slam it down, you're going to get a global motion. You can correct for that.
Exactly.
That's really cool. But slamming a hood is very violent. I would think you need to have high-speed equipment to do something like that.
Right. So what I'm actually going to do is use that light gate there, which is going to be sending a signal when I slam that hood down to our sensor, and our sensor does 2,000 frames per second, which is perfect for the automotive industry.
Okay.
But if we do need to go higher than that with the frame rate, then we can provide proper counters.
Wow. Okay. And it looks like you have a huge measuring volume here. So how big can you get with this thing? This is giant. To
Right.
me, the whole front side you can get. Did you get the whole body side as well?
Oh yeah, of course. So with the ARAMIS system, we can do anywhere from a few millimeters all the way up to multiple meters again. It just depends on what you're looking for.
Nice. So we're going to cut through this whole front side. You're going to slam it down. I'm pretty excited. I'd love to see a demo.
Yeah, that's what we're doing.
Thank you.
CAE groups report to us that durability testing for hood slime failure can be costly and time-consuming, especially to achieve a statistical-based confidence. Simulation methods are currently being considered to replace this physical test. The ARAMIS setup sidesteps these concerns, and it's paramount to the inputs needed for the model. The precise capturing of the time-dependent contact conditions between the components of the closing mechanism are essential in understanding the load transfer between the hood and the body. Through the rigid body motion compensation feature of ARAMIS, the displacement of the hood is isolated and the full motion of the vehicle has been compensated from these results. Here you can see the vectors telling a story of direction and magnitude. What area sticks out to you? To Joe and I, we thought the area closest to the windshield was interesting. We clicked on the surface and selected the Z direction displacement. Then we selected a few points and they automatically plotted on the diagram below. You can see a concentration of deformation and the resulting oscillations of the hood itself. ARAMIS features an operating deflection shape module that can take the displacement across all points in all directions and bring them into the frequency domain. This allows us to view deflection shapes at frequency peaks that stick out to us. I selected 26.5 Hz frequency, and you can see this shape represented on the right, a useful visual tool when considering vibrations. In other door slam projects, ARAMIS has been useful for finding those mode shapes and improving product design. Here is an array of peak frequencies and their respective shapes associated with this door. ARAMIS can be used under the hood as well, so let's take a look at a quick engine study. ARAMIS customers use the technology to measure and verify simulation on many parts of an engine. Perhaps they are interested in an oil drain feed or drain and its vibrations, or they're interested in thermal expansion of any number of components, whether they be bellows, flanges, inlets, outlets. These can all be very important as new turbo engines are developed. In this test, we wanted to measure and isolate the engine during its startup phase. The point marker stickers we place down on the body of the vehicle serve as our reference as we measure the engine top while it starts up. The vectors tell a story of direction and magnitude.
Wow, that was a cool experiment, Joe. I feel like engineering tool ARAMIS just has so many possibilities. It really makes me wonder what else we could do with it.
Well, if you would like, we can roll this sensor to the back of the car and measure the displacements of the lift gate as it closes.
You can just do that. You don't need to recalibrate the system.
Not at all. So this is an ARAMIS fixed base sensor. So what that means is that we can go long periods of time without needing a recalibration.
That's nice. So it sounds like the setup is just patterning and then positioning the cameras. Is that true?
Yeah, so we can do this exact same setup with the lift gate, the body side, the tires, the whole vehicle.
Wow, okay. Just rolling around your lab, taking measurements. That's pretty cool. Let's go do it.
Yeah, come on.
Cool. Okay, it looks good. It looks like we've got target dots all over here. We've got some on the back hatch and some on the body of the frame of the vehicle here. So what kind of inspections can the ARAMIS do for us?
Right, so just like what we were showing with the hood there, we have the dots all over this back hatch, and when this lift gate closes, we want to measure the relative displacements of this lift gate relative to the body. So we're doing another relative motion here, and the cool thing is because we have the dots on the body and on the lift gate here, we can do a gap inspection and make sure that we're still within tolerance when this lift gate closes.
Nice, you're just sort of doing a 2-point distance between these dots.
Exactly.
That's really interesting. So you must be capturing in time. Does that mean you're going to get the velocity?
Yep, because we are capturing in time, we can extract that velocity information when this lift gate closes, and then we'll also track the trajectory of it as well to see that it's path.
Nice. Yeah, I bet a lot of engineers would be very interested in that.
Oh yeah.
Okay. Cool. Thank you.
For this project, we selected the dots for the frame and then for the liftgate, keeping them separate for our rigid body compensation and isolation of the liftgate. For this project, we shut the liftgate 3 times. We wanted to do a simulated design comparison, so we added some weight to the right side of the liftgate to see what happens. The first iteration was with no weight, just a standard close of the gate, and the second we added a 1-pound bar. You'll see those displacements grow larger from the first time. And the third iteration, we added 3 pounds. The motion analysis shows larger and larger oscillations with the progressive loads, as you would expect. Joe had put some stickers on his tail light, so we thought to pick a few dots and inspect them. Definitely some movement during the close of the gate here. We constructed some 2-point distances for inspection to take a look at the gap along the body and the tailgate to see if we saw some changes. And you can see some slight changes as you move progressively through the 3 different iterations. What appears to be happening is the door is locking into place still, and it's just oscillating a bit afterwards. We use the stickers on the glass to isolate the glass surface for an out-of-plane inspection. In the ARAMIS software, you can ask it for minimums and maximums, and it automatically will plot them for a surface. You can see the same trend here. The glass seems to be oscillating in and out of plane, further and further, with the weight being added. Many consumers are unaware, but tires are very complex. Researchers in this space use ARAMIS and computer modeling to accelerate their tire design development process. These ARAMIS tire designers have huge databases of material information from the ARAMIS material data they collect, and they use it in their simulation. However, there are so many variables in tire design that further testing is required to verify the predictions, so that same ARAMIS system is then moved from the load frame to the test rig to capture those dynamic deformations. Here is an example of a Humvee truck speckle pattern on its sidewall. The researchers were especially interested in the deformations during this initial speed up of the tire. Tire construction, especially tread and footprint, are important. With the wrong parameters, the driver could experience harsh riding, poor handling, possibly even noise. In this experiment, ARAMIS was mounted underneath a flat-paned window that the tire drove over, allowing the ARAMIS to view the tread under load. Because it is capturing in 3D, an inspection of the curve of the tire can be made at varying section lines. One of the more unique capabilities of ARAMIS developed here at Trilion is the tire shape measurement. Instead of spraying on paint, ARAMIS projects a light pattern across the surface and collects the shape at moments in time. This has proven useful to aerodynamic groups. Suspension and steering feed forces into the chassis of a vehicle design and play a vital role in the vehicle behavior, including its safety, performance, and overall feel in terms of ride comfort. ARAMIS is a cost-effective approach to monitor these components. Like this shock absorption test, each sticker acts as a 3-axis accelerometer, and the visual results are more intuitive for decision making. ARAMIS is often found in the lab conducting road simulation testing on 4-post test rigs. Or here you can see many points of inspection on a large suspension. Draw your attention to the bottom diagram. You can see a local coordinate system is being tracked. Looking back to the ARAMIS images on your left, you can identify the tire axle as its origin. In ARAMIS, you can track the 6 degrees of freedom of a group of points and monitor rotations during testing. Now let's turn our attention to a rotating part. The next test will involve a cooling fan. The test setup involves placing point marker stickers down in any area we would like a 3D coordinate for tracking. ARAMIS can overlay with CAD or FEA. In this case, CAD was brought in to align with the customer's coordinates. The ARAMIS will capture at 1,000 frames per second to track the movement of the fan throughout. Notice that there are stickers at the center hub. These were used as a rigid body to inspect for deformation of the fan blades. As the RPMs come up, you can see a wobble in the blades relative to the center hub. The user can select any points in this project, and here 6 were selected. Automatically the data for each point will be plotted out in the diagram. This is an inspection of the out-of-plane displacement. ARAMIS is routinely involved with automotive companies to employ wind tunnel testing. These companies often want to evaluate aerodynamics of different components, like the side view mirrors, roof racks, spoilers, grills, air dams. Wind tunnel time is very expensive, and the ARAMIS customers roll their cars in with stickers ready to go as the ARAMIS sits either mounted above on a gantry or off to the side just out of the airflow. The area of computational fluid dynamics is quite complex, and simulations are better than ever. Small changes in product design can have a large effect on airflow fields and overall drag. ARAMIS can help researchers to understand these effects and improve performance in their design. In this performance test, the users place stickers on the leading front cover as a rigid body and stickers along the front fascia bumper to examine the deflection of that bumper. In this analysis, you can see a comparison of sections of that front bumper fascia. The diagram shows as the vehicle comes up to speed, the different sections grow apart. They grow further and further apart, and the outer edge deflects up to over 9 millimeters down away from the front cover. But users can place stickers anywhere on the vehicle and get data. It takes a crew of 2 to 3 people, maybe 15 to 20 minutes to prepare a full vehicle with point markers. In this study, you really can see the flow along the vehicle here, starting in the up direction, that's Z positive, the bottom diagram, and then arcing back down and to the right off the rear of the vehicle. The surface deflections are very revealing here. Whether it's thermal shock, thermal fatigue, or just thermal deformation in general, thermal analysis of vehicle components is very important to the automotive industry. We first capture images of the vehicle at room temperature. Then we take images of the vehicle soaked at 85 degrees Celsius. This can be done through a window or by rolling in the system quickly. Or perhaps Trilion can provide you a housing for your ARAMIS, so that you can have the ARAMIS in the environmental chamber, provided there is room. ARAMIS can be used to inspect for gap change during thermal loading and ensure quality design. But it's not limited to the exterior of the vehicle. ARAMIS can inspect the interior as well. Here's a project with a glove compartment undergoing thermal load. If we zoom into the opener, we can see that this inspection can check for deviations and tolerancing for the product design. Researchers use crash test data to improve the safety and reliability of vehicles. ARAMIS has been used in sled tests, front impact, side impact, seatbelt studies, sunroof crash worthiness studies. Here are a few projects in crash safety. The ARAMIS cameras are positioned at the end of the sled test to capture the full motion of the dummy. Point marker stickers were placed onto the base of the seat to serve as a reference for all displacements on the dummy. Extra stickers were placed on the dummy head to create a local coordinate system for the 6 degrees of freedom tracking. Typically, safety labs will have a witness camera filming their sled test. It gives them qualitative results. ARAMIS takes those images and makes them quantitative. From this test, ARAMIS yielded an understanding of the rotations of the head motion and velocity. You can see plotted out to the right. It also can show the full trajectory of the head throughout the event. In this side impact test, you can see the ARAMIS hanging from above on the left. The B-pillar and roof section was used as a rigid body to compensate for the global motion. This was an impact at about 30 miles per hour. Capturing glass break is not a trivial undertaking. It's very brittle. This is a head impact test into patterned glass, so the ARAMIS is able to track the glass full surface as it undergoes the impact. Sometimes it's just easier to use ARAMIS than it is conventional tools. Take this acceleration pedal, for instance. This is a fairly standard test with easily obtainable results. The ARAMIS setup is just stickers. ARAMIS brings the load in via BNC cable and synchronizes the force. The force versus the pressure of the bar is then analyzed. To take it a step further, our researchers used an ARAMIS touch probe to pinpoint the location of the force. The more analysts know about their part, the more accurate they can deliver their models. ARAMIS is designed for less testing with more data, an abundance of data really. Shape, displacements, strains can all be compared and used as input for the optimization of simulation models. Here is a mock project showcasing how ARAMIS works well with simulation. This is an injected molded part we affectionately call the bumper. The bumper has a fixed support and a load is applied in a downward motion. The ARAMIS is on the left, capturing the reality of displacements and strains, whereas the simulation has its fixed starting position on the right. After the ARAMIS test, a comparison is made between the simulation and the reality. ARAMIS data on the top, simulation on the bottom. A section line is constructed and the displacement across the profile in the y direction is plotted in the diagram. Notice the disparity between the simulation and ARAMIS at the outer edges, nearly 0.5 millimeter. It's quite large. Keeping the section line and just updating the inspection to major strain, the ARAMIS reality data in red shows those same large differences. Then again, across displacement in the z direction, you can see the outer edges of the bumper are simply displacing more than the simulation had predicted. In consideration of our test setup, our fixture may not be the most fixed at the base. If the condition was loosened a bit in the simulation, it may account for the extra displacement. Now the simulation has been optimized to have conditions that are closer to reality, and the results draw closer to ARAMIS data. The now plotted pink line is the optimized simulation. Here is the major strain as it is optimized, coming ever closer to reality. And again in displacement Z across the bumper. This is just a great example of a boundary condition error. ARAMIS works with all major simulation software file types and allows the user to overlay the model with the reality. Full field comparison is very, very powerful here. By using ARAMIS as inputs to your model, maybe just to discover a boundary condition like this, an assumption that was made somewhere along the way, it helps analysts fine-tune their models and get their simulations closer to reality. Moreover, ARAMIS customers report that the data helps to understand their testing. With the ARAMIS capability of referencing itself, it often ensures that the test is measuring what it claims to be testing, providing confidence in the data to both the test engineer and the CAE team.
All right, well, thanks a lot, Joe. I really appreciate your time today, and we learned a lot about the capabilities of ARAMIS, so that was excellent. Look forward to coming back and learning more.
Of course, Justin. We have a lot of interesting innovations coming up on the horizon, so you should really come back and check it out.
Oh man, you gotta leave me with a teaser. I love that. I'll see you soon, man. Thank you.
Yep.
Conclusion, here's a quick summary of ARAMIS. It measures optically and has a seriously fast setup. It gives you data all across the material or part, including the necking area of tensiles. It's capturing strain, displacements, and accelerations at the same time. It can change its field of view just by changing the lens. It's independent of material, time, temperature. It can capture static thermal expansion images or dynamically measure a rotating fan, as we saw earlier. It's insensitive to motion in your project. It's designed to adapt and can help you adapt your simulation to be closer to reality. It interfaces well with test machines, and I really hope that this has been interesting for everyone listening. Thank you so much. Go download the free evaluation software, GOM Correlate Professional, and try out some of the sample files. Joe mentioned there were some things on the horizon. Recently, some of our customers have been using ARAMIS on the test track. Here's an ARAMIS mounted on a motorcycle, positioned to monitor the suspension over terrain. This setup captures the lateral motion effect that a road simulation may miss. Trilion is hoping to have some on-test track projects to show you in the near future. Contact us for details. Thank you very much, everyone.